visiting my place. My name is Alex, and in this session I want to talk about a tool for mutation testing that is built on top of LLVM. But before I can dive into the details, I should first address the question what the mutation testing is. The easiest way to answer this question is by showing an example. Let's say we need to write a function that calculates the sum of two numbers. Obviously, we need to test this function to make sure that the implementation is correct. In this case, we pick two mathematical properties. The test suite, however small, gives us green light. The tests are passing and the code coverage is 100%. All is good. However, there is a problem. These mathematical properties also hold for multiplication. In this case, if we replace the plus with an asterisk as on the right, then nothing special happens. The tests are still green. This change or mutation is not detected by the tests, which means that the tests are insufficient and should be extended. In a nutshell, this is the idea of mutation testing. Introduce small semantic changes into the program and see if these changes are detected. Schematically, it looks like this. You take the original program, add a mutation, run the tests against the mutated program and check the results. If the tests fail, then it's good, because the change is detected. Otherwise, if the tests pass, then something is wrong, either with the tests or with the program itself. This process can be repeated until you cannot come up with any new mutations. Speaking of which, there can be a lot. In mutation testing, each semantic change is controlled by so-called mutation operator. Some examples are replace addition with multiplication, replace addition with subtraction, replace binary operator with the first or the second operand, or replace an expression with a constant. I can easily come up with 10 more distinct changes we can do to the code on the left. Obviously, doing this manually is a bad idea, so we should automate this process. Which we did. I want to present you mul, the tool for mutation testing, which has C and C++ languages as its primary target. Here is a list of items that I consider to be important and worth mentioning. Mul is industry-oriented, meaning that it can be used even with large projects. In such cases, it can be applied incrementally, and in case there is still too much work, this work can be distributed across several machines. Given the complexity of modern software, we are trying to hide as much details from the user as possible, therefore simplifying the setup. Mul's output is deterministic, meaning that it will produce the same results over and over again. There are some exceptions to this statement, but I will cover it a bit later. Also, mul is cross-platform, if you don't count Windows as a platform. It also worked on FreeBSD at some point, but something went wrong and no one had time to fix it. And last but not least, mul is open source and available on GitHub. So you've got the idea, you've got the tool, but there is still a question of why one would want to use mutation testing. The consensus so far is that mutation testing is used to evaluate the quality of a test suite. This statement, while correct, is still a bit misleading and very limiting. Let me walk you through several examples I've seen in production. This example is coming from a proprietary operating system which is used in production in a couple of small aerospace missions. On the screenshot you can see two simple constructors of a four-dimensional matrix on the left and the corresponding test case on the right. The view shows the code coverage report. The numbers on the left indicate that most of the lines were executed more than once. The test seems to be good. But mutation testing shows very different picture. Here, the code marked with red and green colors highlight mutations. Green means that the mutation was detected, while the red means that the mutation was survived or not detected. Most of the mutants in this code are not detected, which is bad. I must admit, when I first looked at this report, I was disappointed. Given that the code has 100% coverage, these mutations must have been detected, which means that mul has a bug and shows the wrong result. However, when I started debugging this issue, I found that mul was right, and these mutations are indeed not detected. The problem, as it turned out, was in the compare double function. For some reason, developers made a mistake and defined the input types as booleans and not doubles. In this case, any non-zero value evaluated to true, and compare double returns false if and only if one of the arguments is 0. The fix for this problem was trivial. I just changed the types and the test started to fail. The most interesting part is that almost all the tests that use compare double function were broken in one way or another. Here is the other example. In this case, the class file represents an abstraction of a file system that has different implementations when you run it on Linux or macOS and an embedded device. The code on the left is just a snippet we are interested in, and on the right there is a simple test case. The test checks that reading a string from an empty file doesn't change the buffer. I guess you can see the problem already. Anyhow, what mal did is basically remove the call to the open as indicated on the right. What happens then is that the getString function calls the read function. The read returns -1 as the file is not open, and getString successfully writes 0 into the -first element of the buffer, but the test is still passing, sometimes. The last showcase I have is less problematic than the others, but it shows another nice side effect of mutation testing. Here on the left is the original code, and on the right there are two mutants with the changes highlighted in bold. Two important things: this is not the real code from production, but its simplified version just to give you the idea. Second, I did not show the corresponding test case, since there was no corresponding test case for this code. What happened is that there were a number of mutations. Half of them were detected, while the other half not. It turned out that any changes to the upper 16 bits of the number did not change anything. The program was only using the lower 16 bits. In this case, we could just drop the dead code and use the int16 instead, as in the lower left function. With this example so far, we've seen an issue with the test, we've seen a potential vulnerability, and we also found some dead code. So I would rephrase the original limiting definition of mutation testing with more broad and correct one. Mutation testing helps finding semantic gaps between the test suite and the software under test. By now, I hope I convinced you that mutation testing has some value. Now let me tell you a few words about the history of this approach. First, the idea itself was mentioned in 1971, but the first implementation has seen the world in 1980, and now it is 2020, so exactly 40 years has passed. I don't really have time to tell you exactly what happened during those 40 years, but I can definitely tell you what didn't happen. Mutation testing did not become mainstream, it did not become popular, and it didn't get as much traction as any other testing approaches. I cannot know exactly what's the reason for that, but my wild guess is that it's performance. So with that being said, let's look at some numbers. To understand the performance implications, we should first understand how mutation testing works. So here is a brief algorithm. Add a change, compile, link, run tests, roll back the change, and repeat. With this process in mind, we can calculate the execution time for n mutants. The formula is simple. Take the time each step takes and multiply it by the number of mutants, and of course sum up all the results. For the sake of the numbers, I crafted an example program. You can see it on the left. What it does is just adds two numbers 50 times. In the middle and on the right, you can see examples of mutations added to this program. In total, there are 50 mutants, each replacing a distinct plus with a minus. I run this code on my machine, and here are the actual numbers. The important one is the baseline. This is how much time it takes to just compile, link, and run the original program. To calculate the naive execution time for 50 mutants, you need to multiply the baseline by 50 and add the time needed to apply mutations. Obviously, in this case, the slowdown is around 50 times. Here is an example of running mal against this simple test program. First of all, the program needs to be compiled with the debug information. Since mal works on the bitcode level, in order to show the results to the user, mal needs to map the bitcode instruction back to the source code. There is no other way other than using debug information. The other important aspect is the -f embed bitcode flag. This option tells Clang to include bitcode into the resulting executable. In the end, we just need to pass the executable to mal and it will do the rest. Here the execution time takes around half a second. If we compare it to the baseline, then the slowdown is only a factor of 6, not 50. If you think that I am over-dramatizing and exaggerating, then I highly recommend reading the following paper. This is an awesome work. The authors did mutation analysis of the Linux RCU module and they used naive approach, which took roughly 3,500 hours of computational time. Now let's get back to the very first example and see what makes mal faster. First of all, with mal we decided to not generate a separate file for each change. Instead, we create a number of copies of the original function with one function per mutation. Besides that, we also store a copy of the original function as well. The next step is to create a function pointer and point it to the copy of the original implementation, as you can see in this slide. And finally replace the original implementation with an indirect call via the function pointer. Now, with this code in place, we can just change the pointer to a very specific mutated function. The question is how to do it easily and how to do it efficiently. The answer is simple, just use LLVM. This is a very high-level overview of how mal works. As mentioned, we are trying to hide as many details as possible. So as a user, you only need to build your program such that it contains bitcode. Then feed it to mal and you will get the results eventually. Under the hood, mal loads the bitcode into memory and starts analysis. It scans all functions and collects all instructions that can be mutated. For each such instruction, mal creates a separate function and applies the change to the given instruction. Once all the mutants are generated, mal compiles the bitcode down to the machine code and prepares that machine code to be executed via a JIT engine. Then mal runs tests against each mutant and collects results, which are presented to the user in the end. I'll now dive deeper into some details, but I won't be able to cover all of them. If you want to learn more, please take a look at the corresponding paper. Initially, we used a naive algorithm for mutant selection. Simply walk over each instruction in the program and collect the ones we can mutate. The problem with this algorithm is that there are many instructions that are never executed during a test run. Think of error and exception handling, or just a code that is not covered by tests at all. We decided to use the code coverage information to only scan functions that are executed during a normal test run. It adds a certain overhead, but it also gives a nice speed up if the code coverage is not 100%. In the end, a change in the behavior cannot be detected if it is unreachable. Previously, I mentioned that mal is targeting C and C++. Even though it works on the bitcode level and can potentially be applied to any other language such as Swift or Rust, the thing is that sometimes the bitcode is way too different from the original code. Here is the simplest example that I can think of. Clang turns integer addition into one instruction, while safer languages such as Swift or Rust generate many more instructions. Currently, mal supports 41 mutation operators specific to C and C++. Here are some of them. Implementing the same set for other languages is possible, but it is much less trivial and would require significant work. As promised, it's time to talk about the determinism. Each test and each mutation is run in a separate process. One of the reasons is that we need to ensure that each run happens in the clean state. The other important reason is that we cannot trust the mutants. After a change, the code can hit a deadlock or be stuck in an infinite loop, or it can simply crash. To make sure mutants do not run endlessly, we put a timeout and terminate the offending process after a certain threshold. Sometimes a mutant can stuck in an infinite loop and crash because of stack overflow. The other time, the same mutant can be killed because of the timeout before hitting the stack overflow. I think I gave you enough details for now. Let me conclude by showing some numbers and also show the progress in performance improvements mal gained during the last 2 years. The major improvement happened when we replaced all the naive algorithms with more sophisticated ones. The other huge improvement is obviously multithreading support. Here you can see what took 3 minutes in 2018 today can be accomplished in less than 20 seconds. I think we can make it even faster, but we'll see where it goes. With that being said, I can only suggest you to give a try or send patches if you hit some rough edges. If you want to learn more about the internals, then I suggest you take a look at a paper or at my previous talk. I guess that is pretty much everything I had. So once again, thanks for watching and take care.
So, hi, and thank you so much for joining the Q&A session of the talk. My name is Sofia and I'm a cryptographer from Cloudflare, and I will be moderating the talk that was given by Alex. So thank you so much, Alex, for the talk, and I will go ahead asking the questions to you. So the first one I see is if there are any suggestions to use the tool Mul for security.
So directly, there is no connection to the security things, but you can definitely use Mul to find those little gaps in between the test suite and the software being tested. So you can definitely find some problems because we did certainly find one in some other project.
Very nice. That would be really awesome, actually, to use in some security libraries. I saw actually that there's already a repository with the tool, and it has lots of requests from the community. So is there some specific features that you will want to add to Mood?
Yeah, there is a number of things we want to add. Just need to prioritize them in the right way. So first thing that we are hitting some limitations of the JIT engine, like thread local storage support. That is being worked on by a guy from, I think, Spotify. They have no idea when it's going to be done, but that's definitely the first thing on our list right now.
Nice. I was also checking the paper that was written about the tool, and there was some note on the paper that it has been a comparison around the different tools that try to achieve mutation testing, and that it would be nice to actually have a research around that. But are there out there any tools that try to achieve the same as Small, and what's the comparison between them?
So there are definitely more tools than just Small, but for C++, I think most of the tools are either they're either coming from academia world. So some of the tools are nice, but they are just written for paper, and there was no further development, at least that I could observe. And there are definitely some other tools for C++. They take slightly different approach. So we work on the bitcode level, and those tools, they work on the source code level. I think there is at least one project that being used at Google. So they use AST-based approach. So they change the source code, and that works very nice, I think, for them. And of course, if you take a look at some other languages, I think every major language has at least one or two tools for this purpose.
Yeah, thank you for that answer. There's a question says, any chance of benefiting from some overlap between leaf fuzzer, sanitizer-based fuzzing, and mutation testing?
I think it's possible to have some benefits from that. So let's say, at least what comes to my mind right now, that what leaf fuzzer does, it provides more input for the function, right, for test, and that can be combined technically, so that to make sure that more things are being executed under mutation testing. But yeah, that just someone needs to try it.
Thank you. And I think this question was basically the same as the other one. It was how do you see the connection to fuzzers? So I think it was the same. So another question, why no Windows support?
I would say technical limitations, right? To not say anything not nice about Windows, but there are also some APIs are lacking. So we use forks to make sure that programs are run in kind of sandbox. And as far as I know, Windows doesn't have this capability, at least in the way we need it. And also we just don't have time. And I think no one on the development team has access to the Windows machine. That's the main reason, I guess.
Nice. Is there a limitation of the complexity and size of the input file?
Not really. So there is definitely connection between the size and complexity, but we did run mal against LLVM itself, against one of the test suits, and that was okay, I would say. So around 10,000 mutants were executed in about 2 hours on my laptop, basically, which is not a high-end machine. So if you have access to some big hardware, then you can certainly use mal on any size of the project.
Nice, thank you. Another question is, if the mutations are applied to the code on the test, would there be any value to mutating the test case code? Does a test case fail if it's modified slightly?
So that, I think, needs to be measured. We are trying not to mutate test code itself, because if we just remove assertion, then it doesn't make any sense, right? But sometimes we still mutate it because we cannot always track what is being mutated exactly. So I don't really have a definite answer for this question.
Okay. And another question is, can the current framework be used to test programs on embedded devices like KIMU?
In the current implementation, no, it cannot be because we rely on LLVM's cheat engine. And if that works on the embedded device, then we can use that. But as far as I know, it's just not applicable in those areas.
Nice. And the last question that I see, I think it was already answered in the same questions of the fuzzes. And I for myself have another question in the sense that over the last years, I've seen some industries, some people from the industries actually using fuzzing techniques for testing, and of course unit testing, but not so much push for mutation as part of the test suite. What do you think would need for the mutation testings to be pushed so it can be implemented on the industry and how developers use the testing suites in the industry?
I would say two things. First, we need proper tooling for that. MAL, however great I think it is, still has some rough edges. So, and the other problem that I would say awareness of people that this approach exists, because I try to talk to some people, and many people I met, they just never heard of this approach at all.
Nice. And the last thing of when I was hearing about your talk, I was also wondering, how do you try to solve the problem of equivalent mutants?
Okay, that's a good question. So I would take a step back. So the core idea of mutation testing that you should introduce semantic changes to the program. But the problem that if we do change something, we cannot know if the semantic has changed or not. And that yields a notion of equivalent mutants. So that means that two changes are essentially equivalent. So just to give an example, let's say you have some algorithm that works on some code, right? And if your input is less than 100, then you use one algorithm, like sorting, for example. If the input is more than 100, then you use some other algorithm that might be slower for that specific number. But we don't know. I mean, technically, we do introduce the change, but there is no semantic difference in the program meaning. And in practice, we don't solve this problem with MAL because I think it's very it's a known problem in the area of mutation testing, but it's mostly tracked in academia because in reality you don't that often, and most of the times you can just rewrite your code to make sure that it just doesn't have this equivalent mutants.
Nice. So thank you so much for all your really nice answers. I don't see any other questions in the app, but thanks so much everyone for joining the sessions and of course for submitting your questions. And of course, thank you so much, Alex, for the amazing talk that you gave. I would encourage you to continue the conversation in the community board of WOBA or in the app or in the roundtable sessions. So thank you so much.
All right. Thanks, Sophia.